Okay, so we can start. Hello. Yeah. Hi, my name is Aleksandr Tavgen, and I want to present, to talk about creating event-driven systems and some problem on that side, some pitfalls, challenges, and some possible things that could be avoided. About me, I have more than 19 years of professional experience. Started as a software engineer and have worked on different fields, starting from microcontrollers and up to developing declarative languages. And I have some hobbies, theater, music. We created a lot of fun projects, and you can read them in Hubble, for example. And I solved some operational and data processing problems in different organizations on a scale. So everything is based on my experience. And what is this talk about? It's not like a documentation reading of some framework, but I will speak about them as well. It's more about general approaches and some overviews, architectural designs, problems on that side, as I said, and some examples in Java. And I want to start from this interesting graph. You can see that world is moving from batch to real-time processing, because you can see how trend of Hadoop, which is famous batch processing framework, is going down, and Apache Kafka, which is one of the base ingredient for streaming real-time system, is constantly growing. Why is it that? Because we live in a world where amount of data is constantly growing. For example, 90% of all data has been generated for the last 2 years. And internet users generate every day this large number. I tried to write some zeros here, but it was too much. We have 5G coming, which is also increase the amount of data which is generated. Competition is going on a fast pace, and batch processing cannot fulfill a lot of requirements. For example, this is quite interesting graph. This is conversion probability. For example, if I'm looking some goods related, for example, to soccer, then probability that I buy something related with the soccer is going down too fast. For example, it's quite high in the first hours. But if you have a processing engine, which, for example, works once a day, then everything that you have is this green line, green area. So the speed of processing is everything. And yeah, we have streams of data. Actually, everything that generates our telephones, computer systems, could be seen as a stream. So what we need today is a fast release cycle. If we want some new features or we want to take more customers, we need a faster reaction. We need a near real-time response. We have cloud-based systems we want 100% uptime and tolerate to failure. So what event is? Event is, we can see as some action, some action or unit of work. You can see it as, for example, some click or some reaction. You can see it as some telemetry which produces our backend servers, and software that reacts to these events, called event-driven. And it gives a possibility to work in an asynchronous way, to decouple different components from each other, and to be reactive, elastic, and resilient. So here is example. Classical request-response system is quite simple. We send some request and waiting for response. Usually this request-response cycle is blocking. So when you send request, you are waiting for response. So event-driven systems communicate using the messages, and actually object-oriented programming paradigm were also oriented on messages, not on a method call, but on sending messages. And this approach gives a possibility to decouple different layers. It gives a possibility to have some sort of replace, and there is a quite good examples. So let's start from year 2011, when Nathan Myers, author of popular framework Storm, which is a streaming platform, published a quite interesting article which called How to Beat CAP Theorem. And here he proposed that all data that we have is immutable. So we need to see our data as immutable facts. For example, if truck was yesterday in Berlin, it doesn't change anymore. So everything that we have, all our data, is immutable. Another quite important point was that our queries, or what we want to induce from our data, we can see it as a function. So we have immutable data, and we have a function over that data. And if we have a so-called pure function, which operated on immutable data, it means that we can recalculate everything. And this is how Lambda architecture was born. So Lambda architecture design is quite complex. There were two layers. One is batch engine, which were built on top of Hadoop, and batch layer recalculates everything, or for example, from some points, all the data that have come. And this give possibility to recalculate everything in case if we have bug in our system, or for example, if we corrupt our data. So it gives some sort of safety for operational and for engineers. And there were second layer, real-time engine, which was not so important and can have some flaws. I mean, some events could be lost, and some events could not be processed. I will show why. And there was a certain backends where all the data after calculation can be shown to the operator. So this was quite interesting approach. It worked. I know several startups who built their products on top of that. But the main problem was the batch engine, because actually we can work directly on streams. So here how Kappa architecture was born. So here everything is in a stream, so all the data. All data is immutable. Single framework, single pipeline, and which is quite important, it has replay possibility. For example, if we have all the messages in Kafka, so we can replay everything from the scratch. The same way as we can do with Hadoop in the batch layer. But here, if we go further, we can see that our system has two layers. One is like command, which change the state of the system, and second one is a query. So this is called, CQRS. So command query responsibility segregation, which means that two pipelines were separated. One, which is change the state of the system, work in a so-called stream mode, and it's called sometimes even sourcing, and querying was separated from that in a different line. So we can see that event is an internal states change. Command in this system is also event, and using this approach, we can build system which can have quite complex logic. So let's take some Lego pieces, for example, to show how such systems could be built. Usually, we have some sort of append immutable log, or it could be a messaging system, for example, RabbitMQ, and some sort of processing engine. Usually, we know Kafka everywhere, but Kafka have some flows. The main flow is Zookeeper, and they want to drop it soon. But Kafka is quite good because we can scale it, and we can process a lot of events in a parallel way. Kafka is good because we can store all our messages, I don't know, forever. For example, Plumber company stores all the events from starting the operation, I guess 3 years, 4 years, so they can replay everything from the scratch if they want. And which is more important, it gives a possibility to data agnosticism. What does it mean? It means that anything can send some events here. It could be Internet of Things, it could be some services metrics, it could be transactional data as well. And on top of that, 7, 8 years, there were rising of processing engines because there is a common patterns working with the streams. A lot of engines. Storm, which author was not on Mars, Apache Flink, Samsa, Kafka Streams, all they have much in common. And usually they use some sort of functional approach and creating declarative pipeline. So the same way, for example, as we do in Java. And all these frameworks oriented on scaling, because again, we live in a world of web scale system and complex event processing. So there is some general problems working with the streams. And if we take some common patterns for such systems, then usually it's preprocessing of some data. For example, we have some some sort of data, and we want to enrich that, to add some metadata. This could be alerts or thresholds from telemetry, from metrics, from, I don't know, Spring Boot applications. It can be application rolling with window, which means, for example, we're calculating some average or some variance. It's widely used in machine learning, and we have some sort of system. I will talk tomorrow about a system built on top of streaming system which used machine learning. Online control, joining streams is quite important things because, again, we can aggregate data from different data sources or data centers, and tracking. Tracking is quite popular today as well because a lot of startups, a lot of companies right now try to optimize, for example, logistics. They collect data from trucks from Europe and try to optimize roads. Or, for example, Bolt, which is Estonian company, widely uses tracking with machine learning to predict, for example, estimated time. And quite most interesting part is complex event processing, which is focus on detecting relevant patterns in streams. For example, if you have some sort of alert system, you have some sort of rules, and you want to match against these rules. Usually, it's based on some sort of state machine, usually non-deterministic, because there is a problem with the working in a distributed system, which I show. And conditions usually defined with a domain-specific language or creating some sort of abstract syntax tree. And this is quite common case for application of machine learning, which is quite successful in this case. So let's start from the problems. The main problem here when we work with the distributed system in a distributed world is CAP theorem. And usually we can say that you can choose between availability or consistency because we have already distributed system. So I want to show that in case of a streaming system, CAP theorem is not binary. It's not like you choose availability. It's not like you choose consistency. For example, let's take some stream analytics with sliding window. So here is our window, and all coming events are going here, and there is some sort of mass calculation, for example. So welcome to distributed system. We have, for example, different systems distributed all over the world, for example, Asia, Europa, whatever. And we have events that are coming to alerts event manager. And these events should generate alert. Imagine we have a network problem. So one event didn't come. So condition weren't met. So we have no alert. And event finally came to our system. For example, network failure. So what we have? We have event which came from the past. So it means that our window should calculate not only the past, but possible future. So how long this future window should be? Don't know. But again, the more unstable network you have, the more problem from the so-called time machine window you have. Another case is, again, consistency versus availability. So, as I said, for event-driven system, CAP theorem is not binary. And we usually have two sources of data. One is transactional one. We do not want to lose anything because it can be some payments information, financial operations, so we want to keep everything. And some sort of analytical data, some events from telemetry or some sort of clicks which could be lost. So again, data can be lost and data can be lost. It's quite similar to TCP UDP protocols, and the same trade-off. You have performance or availability. The hardest one here is a problem of exact ones versus at least ones, or as I want to say, n, exact n, or at least n. Let's see a small example. Here is a code of complex event processing system, which aggregates events with violation. So imagine we have some sort of monitoring, we have some sort of events which came from different parts, and if events are matched against some rule, for example, one value is above one value is above 100 and another less than 50, then alert is triggered. But we have a substantial problem out of order arriving in network. And here is quite simple test, which I want to show. This test takes set of messages, shuffles them, and tests against the rules. You can see that amount, I make it larger. You can see that amount of matches is quite different. So we have a 12, 10, 11, 10, 10, 12, 11. Sometimes it's 9, 8. So out of order gives every time problems with if you have some sort of complex logic on your stream engine. So one thing which you see working in with a streaming system is a functional approach. So all the frameworks starting from Storm, Apache Flink, Kafka Streams is oriented on functional declaration. So you like create a pipeline using a declarative approach. So why? What's the problem? The problem with the classical object-oriented programming is that you have some sort of object which encapsulates some state, you have some sort of interface, and problem is that when you operate with the objects in concurrent way, then object state invariant could be broken. So everybody knows the race condition, deadlocks, so there is a lot of things how to treat all that things. And another thing is object-oriented programming oriented on nouns. So like me, dot walk to store, open, basket, added, milk. Functional programming is oriented on verbs and focused on functional composition. It means that if we have functions, pure functions, combined, chained together, and this function is so-called pure, or we can treat them as a pure, then as a result, we will have a combined function which will have the same characteristics. It has some performance implications if we work with mutable data, and we can lose some performance on copying, but it has great benefits as well. and it's oriented on verbs, like walk, open door, add basket, milk. So even in designing of such system, it's easier to break functional execution paths on verbs. Another quite important thing is lazy execution, which means that we define our execution paths before the real computation. Here is some functions, but again, it could be services, it could be microservices, it could be some functions as a service, whatever. But for example, if we have a function which always return the same output on the same input, then we can optimize this quite effectively. We can cache it, we can have some pre-calculated values, and again, it is quite useful and declarative. So here, I guess it's quite small font size, but again, here is code from different frameworks: Apache Flink, Kafka Stream, Samza, Storm, and you can see quite common idioms here as well. Map, group, split, flat map. So topology of calculation, topology of stream processing is defined as functional composition. So going further, we can see processing service in an engine as a function as well. So again, we can cache it, we can have some optimization on that side, output defined by input, and even in case of out-of-order arrival of events, it's also true, but we will just have different results. A lot of frameworks, as I said, use this approach, and our system evolving in time. And this could be a problem, because, for example, if startups, we're working on stream processing, when we make analyzing of some data, then we have new features, we added new semantics, we added new fields to, for example, our messages. And this make a problem for replay. So how you replay 3-year data. Everything is changing. And for example, this is same example about what I said. Kafka, I know some companies have 25 versions of schema or 47, and there is 2 approaches. For example, if you have a new data type and you should define new schema, you can create new producers, but it will lead to proliferating of producers, consumers. You will have 47 consumers, 47 producers, and your replay function is almost unusable because, again, you should control and manage all this amount of code. And another approach, which is quite important in functional composition, that we can use approach of pattern matching, where you do not need to create every time a new producers or increase amount of them, but again, defining a functional pipeline, you can add your features in a more elegant way. So here is quite a simple example of topology built in a Storm. And you can see here again, quite complex calculations defined, and framework takes the responsibility for scaling it up or deploying functionality on different nodes. Or, for example, another quite common architecture of complex event processing, where we have some operators on data which is functional. It could be on one node, it could be different nodes, it could be different services, and it's quite easy to set up to set up stream processing as a functional composition. And here we can talk about reactiveness, because they are going side by side. Reactive manifesto is quite simple. Responsive, we want that our systems were available. We used message-driven approach for that, for decoupling components. We want that systems be resilient and elastic. In case of increase in load, we can easy to scale it. So we have like two sides of a coin. Functional one, where we're building software by composing pure function, avoiding shared state and some side effects. On the other side, we have a reactive paradigm, which is asynchronous and oriented on the propagation of changes. Working with Java, we have a streaming KPI, and we can think that it's quite similar, but not. So Java type streams are oriented on pull model. So consumer ask for the data. So in a reactive approach, in reactive paradigm, data is pushed to the consumer, and it gives a possibility to have a more flexible solution again, because we can propagate this pushing on data on different nodes. One of important thing in processing all these things is, as I said in the beginning, is the blocking requests. For example, in classical systems, you have a request and you have a response, and your thread or your executional path should wait for that. And again, if we have some resources of threads, then we are limited to the amount of so-called blocking requests. In non-blocking processing, we have some sort of event loop, which can send request and park so-called executional path until response is returned, which give quite great possibilities to build performance system. For example, this is example in Java, which is so-called Haskell style, which implements breadth-wide search on its take a matrix and creates graphs of this matrix. So it has a lot of requests to database, then responses combine it with another conditions, send it again, and all responses is chained together in a recursive way. So why is the main goal of all this if I'm not a Netflix? Actually, it's all about to maximize use rate of our modern multi-core CPUs and threads for competing for that. I want to show you some small tests, similar logic, more than 2,500 units of work, which is database request and some computational intensive work, scheduled once a minute. Execution on a thread pool with blocking driver takes 30-35 seconds average. And let map this logic on threads and on reactive pool. So here, 1 unit of work, 1 execution path is mapped on one thread. You can see how high is and unstable CPU because of increased context switches. There is some timeouts as well, and quite large memory disturbances. Here is 8 threads with non-blocking I/O. You can see that CPU usage, that context switches are almost gone, and code is hotspotted. You can see how flat is memory usage, and everything, if we talk about the calculation, is quite uniform. So again, here is a picture of two approaches. It means that one reactive instance can load DB much higher. For example, if we have 1 DB, which is optimized to work in a synchronous way, we need, for example, 10 instances of application to fully load our DB. So one instance based on reactive approaches can fully utilize 1 DB instance. It's quite useful because if we develop an application for streaming which process some data flow, then we can quite effective use database and application bound together. And if we use some orchestration engines as Kubernetes, it's quite easy to set up such kind of system. So here is quite a small example of such system where one service is quite coupled with a database, and everything is working quite effective, and some data flow processing is going further and further until resulted in some BI information or alerts. And if we talk about such things, then again, all these services can be seen as a function. It gives an easy way to scale it, because if we have an increased event stream, if we have an increased data load, then we can add the similar function to our architecture. So here is summary where most important thing is think in one paradigm. Think in paradigm of architecture, create a functional composition of your services, or build it using modern frameworks, which is also declared using functional approach. Use reactive where it's possible, and reactive is quite effective. It can give to you 15, 20 in performance increase absolutely on the same machine, on the same configuration, out of the box. And again, if we think functionally in creating our system, we are avoiding mutable state, then we can have a quite effective results. So Java actually is quite still a good candidate for that, and modern Java reactive drivers, reactive sockets can hold quite large load even on a quite small machines. So tomorrow I will talk about observability system which we built, which used machine learning, which is stream based, and here a lot of things which I talked now will be explained more. So thanks a lot. If you have any questions, this will. Можно по-русски?
Thank you. My question is a little bit silly. What is the difference? Can you explain the difference between, for example, Apache Kafka in streaming and the simple queue like RabbitMQ or in-memory?
So you mean your Kafka streams?
Yeah.
So Kafka streams is framework built on top of Kafka. So this framework gives a possibility to declare stream processing, and you don't need to think, okay, I take data from this topic and send result to this topic, and somebody take from this. So it's quite complex. So Kafka Streams gives a possibility to describe what you want in a declarative way, quite similar as, for example, which we use in the Java streams, and gives us out of the box. RabbitMQ, if we talk about this, is just a message queue or message provider. Yeah. So.
Okay, and second question.
Yeah.
Can we use this approach of streams in using like in Golang channels, non-blocking channels? I mean, with a buffer. Yeah.
Yeah, I forgot to say, yeah, because if we talk about reactiveness and reactive approach, it actually uses a lot of paradigms. For example, Erlang, Elixir, or Akka streams, where we talk about actors which exchange messages. The same communication sequential process, which is based for Go channels, so it's the same way asynchronous Kotlin coroutines. So the reactive paradigm or approach, it's quite general, so there is different ways of implementing that. And Go is quite effective in that way because, for example, the same database which we use quite actively in InfluxDB is written in Go. And effectiveness or amount of writes that it can hold is just because it can very effectively work in concurrent way with different streams of data.
Okay, thank you.
Aleksandr, thanks a lot for your presentation.
Thank you.
It was very informative and helpful. Thanks a lot. We will continue emerging in the software architecture in 15 minutes here at 3 p.m. Next speech. Thank you.